Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Rocket Monday, we're going to talk about nuclear electric propulsion. So let's dive deep into it. So what exactly is the problem? Well, problem is as of now, as in year 2025, if you want to basically figure out how far humanity has reached, well, at this point in time, if you are a person and you want to like, hey, I need to go to low Earth orbit, it can be done quite quickly, especially for human. It can be done under a year or maybe even a few months if you are well connected. And if you are talking about payload, it can be done under a week if you are well connected. So we have reached a point where it is cheap and it is quick to travel to LEO. LEO part is sorted. And what about above that? Let's say the another interesting part, that is geosynchronous orbit. At that point in time, you have two options. Now we are going down in the quality. So you have either expensive option that is very quick, or you have slow option that is cheap-ish. For example, you can have a electric ion engine system and you dump the big heavy geostationary satellite in low Earth orbit. Again, cheap, but it will take 6 months to raise its orbit utilizing ion engines so it can go to geostationary. Again, for some satellites, it's minor inconvenience simply because they're meant to run 10 years. Other companies are like, you know what, let's use hydrogen, that could get them quicker. Or they're like, you know what, time is so important. They're like, you know what, bigger rocket. So we have, you can see, we like in low Earth orbit, we got this. We have all the option. The moment we go to geo, it's like, yeah, you have to make a choice. Do you want a very expensive fast rocket? Do you want to have a lot of propellant in your satellite itself so you can do orbit raising quickly? Or you are willing to wait 6 months to deploy the satellite? Like the satellite is deployed, it's just like to actually be deployed. So you can see like our quality drops off very quickly, and anything that is further than moon, right now moon is super expensive, and you can do it with cheap. Like you can take Saturn V and yeet something there in 3 days, or you can take PSLV, which is a very small rocket, polar satellite launch vehicle of ISRO, and it takes 6 months. So it is doable, but the moment you go above basically moon in terms of distance, basically anything that is more than 2 light seconds away, yeah, God help you. So at that point in time, flat out, we do not have a viable technology. Basically, how easily you can dump things in low Earth orbit versus how quickly your tonnage shrinks. Basically, the payload tonnage shrinks the moment you go above moon. You would be shocked. Like it's not like, oh, linear drop. It's like, shwee, done, nothing. So fundamentally, that creates an issue. Basically, Mars or anything with enough tonnage is flat out not viable. Basically, even sending 1 ton of rover, it's pushing it. Like that's how difficult it is. So what do we do right now? We do have missions which has reached to Pluto. So how do we do it? Well, we just throw and pray. There is nothing more to that. We just have a rocket, we fire as hard as possible with the kick stage and just hope that it goes. And be mindful, that's another penalty. We are sending it so fast and we do not have any actual thrust there. It's just like flyby. Like, can you imagine, like you spent 10 years and all you're gonna get is a flyby. It's not even orbit capture. Why it's not orbit capture? There is no way to decelerate it. So fundamental chemical propulsion fundamentally seriously can't do anything above lunar surface. Like the moment you want to do mathematics, like what kind of propellant we have, yeah, the moment you type in the equation above Mars, or basically 2 light second, 10 light second, yeah, the answer is like lol. So fundamentally, Mars colonization cannot be done on Starship. Like, but we can launch it. It's like, no, first, Starship has not even reached orbit yet. And the most likely culprit for that is why they are not deploying payload. Even 9th time is simply because it's too goddamn heavy. The dry mass of the rocket is too goddamn heavy and they're pushing engine too hard. And if you push engine too hard, it goes kaput. So, and again, they know this. That's why the Starship's original design concept utilized carbon fiber, so dry mass was low enough. Even Falcon 9 utilizes lithium aluminum alloy. But if you want to do this much with stainless steel, it's like, yeah, you're getting temperature resistance, but you are compromising so much more that it's like it's just not reaching useful level. But again, let's just assume they successfully completed it. Can it actually go to Mars? In principle, yes. But can you have enough tonnage in Mars? No. No. And again, that's why like they always show, oh, we have this one docking and we're going to refuel it. It's like, you have to do that way too many times, like upwards of 20 times for one. And now Elon Musk smokes and is like, you know, we're going to have launch every window, we're going to launch 1000 Starship. I'm like, 1000 Starship multiplied by 20. You're going to burn a hole in the planet, in the basically upper atmosphere. And again, some people are raising concern that it is not that good for the ozone layer. So fundamentally, you can't. Like, you can force it. It's a really bad idea. It's literally like using a flamethrower to light a cigarette. Not a good idea. So that's the problem, fundamental on physics level. So why do we have this limit? Well, it's all about mass and velocity. Whenever you're talking about rocket, you are generally talking about this puppy, rocket equation. Now, if you want to simplify this, understand in this way. It's what about how much you are throwing and how fast you are throwing. So basically you are throwing a bag, and that bag, ideally you want it to be as heavy as possible. So you're like 5,000 ton, I'm throwing it. And how fast you want to throw it? Just a little bit slower than the speed of light. That would be ideal scenario. That would be like Starship level scenario, like Star Trek and Star Wars kind of scenario. But we do not have that kind of oomph or technology. So if you have throttle, basically I can increase the mass or I can increase the velocity, both will give you something. So ideally you will increase both of them. Basically you'll have as much thrust as possible because you have bonkers amount of mass flowing through. The mass flow rate is bonkersly high, and the exhaust velocity is also stupendously high. So that way you can get best of both worlds. But engineering is like, nah bro, we are not there yet. We don't have hyperreactor reactors. We are not there yet. So what's the next best thing? Boost one. For example, a solid stage booster, basically kick stage or this sort of thing, generally use solid booster. Why? It has mass, like it throws tons. It's like penalty, it does not have specific impulse. It's very slow, like exhaust wise. Benefit, it can yeet you from the basically low Earth orbit, so to say, and even surface. It can just yeet your ass because it is powerful. Like basically, if you want to move tonnage, like from gravity, solid booster is like, I got you. That's why ICBMs have solid booster. It's like very powerful. Liquid has, but you have to have a lot of rocket engines. So mass gives you thrust. Basically, if you are increasing the value, mass gives you thrust, think in that way. And exhaust velocity gives you speed, meaning the moment you are at low Earth orbit, now your throttle changes. Basically, you do not need that much thrust, but you need bonkers amount of exhaust velocity. So that is the one thing. And the moment we are talking about interplanetary distance, you are talking about something that exceeds 2 light seconds. Yeah, at that point in time, speed matters far more than thrust. You can have something that is like micronewton of thrust, still okay, as long as it can give high enough velocity. Now, chemical engines are just too goddamn inefficient, and that's why even reaching low Earth orbit, you have to require multi-stage rockets. It's just too goddamn inefficient. Basically, this line, basically engine exhaust velocity is not high enough, and it's not thrusty enough, so to say. So now, thankfully, rocket equation does have the trick that it has a logarithmic drive to it, meaning you can exceed the velocity of your exhaust. It's like, wait a minute, how is that possible? Well, think in this way. Your car is moving and there is no resistance around it, no atmospheric friction, and car is moving 100 kmph. You threw something that is at 100 kmph. You threw it at that speed. What happens from the outside observer point of view? It's moving at 200. So that same happens with rocket. But again, it's a logarithmic curve because again, you have to calculate the initial launch mass and the dry mass, basically the final, once you have depleted all the propellant. So that gives you the curve. And this is the final dry mass. That's the problem with the Starship. It's too goddamn heavy. And again, that's why they're jettisoning the cap, so to say. It's too goddamn heavy. So now again, if you can't make this basically dry mass as lighter, you want to increase the exhaust velocity. But given the fact of chemical energy, it's limited. Even 5 km/s is like good. Like you can't expect too much more or too much little. So more or less, this is what you have, and this is the curve you're gonna get when you are burning the rocket. So fundamentally, we reached a point where it's like, yeah, chemical, we got it so far, but it can't take us further. So thankfully, whenever we have to do really deep space mission, we utilize ion propulsions. Now, ion propulsion also has the same equation, but it has bonkersly high exhaust velocity. So exhaust velocity, instead of 5 km/s, it could be 15 or 5,000. It's like, is it possible? Yes, it's just not done that. It's like melts the reactor, but it can be done. Basically, you can have ludicrously high exhaust velocity, like 21 km/s or even 30. So you can have bonker, because you are ionizing a gas and its mass is very low, but you can dump energy via electrical coupling. Basically, you have electric static field that is causing that. So you can yeet that puppy. And again, we do that in Large Hadron Collider. We yeet things at 99.9999% speed of light. So we can yeet things as long as they are light enough. So ion engines utilize that. So their fuel is some sort of noble gas. Argon if they are cheap, krypton, xenon if they are expensive. So that has that. Now here's the penalty. Thrust is negligible. Like I can do like this and nothing will happen to me. It's like, bruh, I don't even notice it on Earth's gravity. But when you are in space and there is nothing that is slowing you down, it starts to pile up. So this line slowly starts to go up, and it goes up. How much? Meaning, if you have the same amount of mass and you just yeet with the kick stage will give you velocity. It will give you acceleration. It will be like almost 1g or 2g is possible. So that is the benefit of kick stage. You're just gonna go kaput. Like all the boom happens very quickly. It's just like, whew. So you drain all the fuel, you get the speed, the end, and now you're coasting. Like you're just waiting for Pluto to happen in 10 years. But if you have ion engine, you are starting very slow, like very, very slow. At 1 million kilometers, you are still behind. At 2 million kilometers, you are still behind. But by the time 5 million kilometers starts to happen, you start to catch up. And by the time 6 million kilometer happens, you're starting to chase it down. And by the time 10 million kilometer happens, it's like, bro, you are going so much faster. Like, to give this ESA, this is a very awesome example from ESA. It's like, by the time 5 million kilometer happens, you're almost reaching it. By that 6 is like, yeah, you have taken over. So the further you travel, the faster ion thruster becomes. And again, you still have fuel remaining. So what is the gap? 10x. Meaning if you have the same mass, ion engine will travel 30,000 kilometer versus 3,000 kilometer. So that's the whole point. 3,000 versus 30,000. So 30 million kilometers. Oh, sorry, kilometer per hour. Yeah, 3,000 kilometer per hour versus 30,000 kilometer per hour. So that's why you get bonkersly exponential benefit simply because of your exhaust velocity being stupidously high. So that kilometer per second, you want that stupid high. And you're like, okay, what if I just have a torch? It will work, but it will have so low thrust, it will take like, 15 years to accelerate. So there is a compromise. So nuclear energy has dense enough power rating where it can actually do that. Because again, can you do with solar? In principle, yes. Problem is just that you will not get anywhere because solar panels will be heavy. So that's why we need something that inherently has a lot of energy density. So nuclear is the best solution. That allows us to take care of all of this part. Dry mass does not become stupid high. Why? Because nuclear energy is fast enough. Your initial launch mass and dry mass does not change because again, even if you are moving hundreds of tons of craft, you barely will have few ton of propellant. But your exhaust velocity, this vector goes YOLO. That exhaust velocity is YOLO. So your change in velocity becomes very good. So these are the physics level limitation. It will not change whether you are in 1950 or year 5000. It will not change. So the first time people actually were serious, as in during JF Kennedy era, they were like, okay, moon is cool, we got this, we have the technology, math says we can do it. But they knew back then also, but math will not allow you to go to Mars. It's just like, no. You can throw things, but for human, no. So that time, nuclear thermal technology was created. Basically, the idea was you're going to take liquid hydrogen and you're going to fry it over basically an active fission reactor, not plutonium or like a radioactive decay, an actual fission reactor, and you're going to get heat energy out of there. So that time your specific impulse will go up from ideal scenario of 465 of liquid hydrogen and liquid oxygen to 900. You're going to basically 2x that puppy. So the idea is you take the heat, you do phase change of liquid propellant, and then you superheat that puppy, and then you get thrust. Now, if you have a temperature, right, let's just say you have 2000 degrees Celsius of a reactor, the mass of the propellant directly affects the exhaust velocity. Basically, if it's a heavy mass, basically water vapor, let's just say H2O. H2O is heavy. It's like going twing. But if you have something lightweight, let's say hydrogen, it goes kaput, even though the temperature did not change. That's why you want low molecular weight propellant. That gives you the best specific impulse. And again, we are talking about going more than 2 second light second. So fundamentally, you do need better specific, more than you need thrust. Because again, you can have your small chemical propellants to just do course correction and all that. But when you need that really long range capability, you have to utilize hydrogen. And you can carry a lot of liquid hydrogen. You do not need anything else. That's the good part. And again, hydrogen is not that difficult to store if you are in deep space. So liquid hydrogen, and you just boil it in the reactor. So some designs had that, liquid will flow from the outside acting as a first layer of coolant, but by the time it will become gas, it will go through the core, superheating, and then just going kaput out of there. So it does work. And the thrust is actually good. Like for an upper stage, it's actually as good as a kick stage. So that was another benefit of it. It's not like ion engine which just has efficiency but does not have the thrust. It has thrust. Like it can take you from low Earth orbit to lunar injection burn or to low Earth orbit to Martian burn. It can do that. It has that kind of oomph, basically kilonewton. It has that oomph to do that thing. And America, when this project was greenlit, they actually built nervous system. Basically, they built it. That was the design concept where they're like, okay, how the heck you actually go to Mars and come back? Not the Elon weird where it's like, we're going to go there and you're going to be dead there. It's like, no, go there and come back. So that's why they built this sort of concept. And they actually built it, tested it. That's 900 is not theoretically, they actually achieved it. So that's the whole point of it. You get 2x the efficiency, and it can basically, the rocket's still massive, but it will give you basically time shrinkage from 9 months to 5 months. So that's the proportion, how much shrinkage you can get just going from 400 to 900 in terms of fission impulse. Now, they knew this was still pushing it, and there were some other designs where like you had molten core, that puppy can give you 2600, and there were like gaseous core, which was stupid, that was 6700. I don't even know how the heck they theoretically came up with that, but on paper it was possible. But again, they built the solid core one, and it was built like, it's not just like hoo-ha. No, they built it, tested it, and the project was cancelled by Nixon, I think. So, and again, this project never actually dies, because like then they come up again recently by DARPA, and they're like, okay, we're gonna do Draco mission, and then they cancelled it again because of budget cut. It never ever lives, never ever dies. So this is nuclear thermal technology. Now again, much better than any chemical option by 2x, and does have significant advantage, but it has upper limit. Like 900, good, but what if we can do better? Not just stupid better, where it's like a molten reactor. It's like, no. What if you can do better? So we come to nuclear electric system. Now, why is that? Well, using nuclear fusion reactor, not just a heater, a reactor, you can convert the thermal energy into electrical energy. Once you do that, you can drive an ion engine. Why? Ion engine exceeds what you can get out of a hot exhaust. It exits because it's using electricity, or heck plasma, or heck microwave induction. You can go YOLO. Basically, you can have exhaust velocity that is stupendously high, not just high, stupendously high. So you can get bonkers high specific impulse. How high? 2000 is bare minimum, meaning all the designs are like, if you are getting lower than 2000, you messed up. So 2000 versus 900, that's like, shut up, take money. Now be mindful, that time ion engines were not developed yet. So of course they did not know about it. We know about it. So with current ion technology, 2000 is like, you know what, that's argon. That's like cheap gas. If you want to do a Mars mission, you can afford krypton. You will get much better than it. 2600 should be easy. It's like, take it and go. So you have a reactor. That reactor creates electricity. Electricity is utilized for fuel ionization, and that gives you your thrust. So this is a normal thing. However, you have to understand fundamental limitation in this is that reactors are not efficient from converting heat into electricity. They are not efficient. On Earth, they are not efficient. Basically, most of the energy is still in heat. It's not in basically waste heat, but you're not getting too much electricity out of it. That's a problem. And unless you have Iron Man reactor, this puppy that he has, and how the heck he does not get fried when he has a reactor, he generally is running what we call aneutronic nuclear fusion. So you get charged particle as emission from the reaction that can be converted into electricity directly. We haven't built that technology yet. So this is the next best thing we have. So what about efficiency in this design? In this design, if you have a reactor, which we can make a very small one. And again, reactor could be super small. It's the containment that is the expensive part. So reactor is small, and the Stirling engine, that's also small. But how much conversion efficiency you're gonna get, that depends on the T delta, basically how hot this puppy is and how cold the radiators are. So if the reactor is super hot, let's just say 700 degrees Celsius, and the cold end is 500 degrees Celsius, it will work. You will get energy, you will get continuous energy, that's good, awesome, but you will not get efficiency. But again, nuclear fuel is not that expensive nor that heavy, so people are like, you know what, not necessary. But again, you can improve it. Even if, let's say, your radiator temperature is locked to 500 degrees Celsius, you can't dump more energy than that, so 500 degrees Celsius, but you can make it hotter. Let's say you make it 1500 degrees Celsius. I think that's the upper limit I've seen some reactor designs. It will improve your efficiency. But again, given the NASA's kilowatt reactor design, you generally do not want to go that high. You want to make sure that even if reactor left running, none of the metal should get kaput. So you generally want the hot end to be around 700. So high T delta between hot and cold directly gives you conversion efficiency. So 30% plus is not possible in vacuum, because again, vacuum is a perfect insulator. It requires an ocean to cool a nuclear reactor. And again, that's why we have giant cooling tower, like bonkersly huge cooling tower, and they consume water like there is no tomorrow, because it's the cooling part that's the difficult. And if you are surrounded by perfect insulator, yeah, it's difficult, meaning the T delta between basically the Stirling engine hot side and Stirling engine cold side is not that much, but again, much better than thermoelectric generator, and efficiency wise is also much better. So fundamentally, this design does work, and again, NASA does know this. That's why they built the kilowatt reactor. And for the coolant circulation and all that, they first came up with the fluid flow, and they're like, yeah, that's stupid. But then just use heat pipes. Heat pipes have no moving parts, so it can work. Although the Stirling does have moving parts, but it does work. So this is the best technology as of now. Humanity has it in arsenal that can allow us to go to Mars very quickly, and no magical technology required. But you do need bunkersly large radiator. That's the penalty of it, and that's why you want the hot end, basically cold end, to be high temperature. The hotter it is, the smaller the radiator size. Smaller the radiator size, lighter your craft, faster it's gonna go. So that's the nuclear energy part of it. So the only actual reality that we have, that we can actually go fast enough, quick enough, so we're safe enough, and actually have enough energy to come back. So that's doable. That's another aspect of going with ion engines. You can have enough propellant to go circle around, do orbit, orbit correction and all that, and then come back and still be chill. Like, we good, we got this, we got this. So that's the whole point of nuclear electric propulsion. And again, specific impulse 2000 is starting point, meaning if you are going below that, you messed up. Like 5000s are the Casimir engine designs, are just like, tada, we are testing it, it's going there. It's just that it needs superconductors and bonkersly large amount of electrical energy. Superconductor is not hard, given the fact that Japan exists and they have a maglev train and it has superconducting magnet that does not require recharging. So they have a helium bottle that keeps the superconductor, and then they have liquid nitrogen bottle to keep that bottle cool, and they just chill. And imagine that bottle in space, it will be super chill. So it is doable. It's just that radiator is the limiting factor. Basically, how lightweight of a radiator you can make and how large of surface area, because again, you do not have any other thing than photon emission, so you do need surface area. You don't have airflow. So that's the nuclear electric part of the only scientific option we have. So what are the hurdles on it? Well, this graph is the hurdle. Again, I have linked a very awesome video about this whole topic in detail, but the core concept is, the cooler you want, basically, oh, I want my reactor only go, let's just say 500 degrees Celsius, but I want the cold end, of course, it has to be at least 200 degrees lower, 300 degrees Celsius, your radiator size goes bonkers. So if you want your radiator size to be logical for certain megawatt amount of energy dumped, you do need higher temperature. That's the issue. You want, it has to be. Otherwise, the radiating area you need has to be super huge, so it gets cool enough. Or if it can glow, that's awesome. That's perfect. That's what you want. So fundamentally, a reactor can easily work. Cooling the reactor, again, NASA has sorted this part. It's doable, because again, the cold end of the reactor is 800 Kelvin or 527 degrees Celsius, somewhere around here. So this part is sorted, because again, you can have a reactor design, you have sodium heat pipes that can easily work at that temperature. It's like, bro, we good, we got this. Stirling engines, we good, we got this. Steel is like, bro, 700 degrees Celsius, like, I don't even warm up at that. It's like, we good, we got this. So, but now we come to the trickier part. Everything else, again, you must have seen ISS also consumes a lot of power, but again, it's not megawatt, it's kilowatt. And let's say you have 10 kilowatt of electrical generation, and all 10 goes into the electrical propulsion part. Problem is, no propulsion system is 100% efficient, no electrical one. So even if it's converting only at 50%, yeah, now you have a lot of megawatt of heat to dump in. And here's the problem, that's at lower temperature. You no longer are here, you are here. This is the problem. This is the main issue. That's why if you see any NASA's design, they have bonkers amount of radiator. It's not for the reactor. Reactor is like cool, because again, it can handle hot. Is the electronics. Even the highest rated capacitors are like, what, 105 degrees Celsius or maybe 150 degrees Celsius. Imagine the whole electrical unit being kept at that temperature. It's not viable. So that's the main issue. We do not have hot electronics that can handle that. And again, ideally, you will have a basically propulsion engine that is very efficient, or all the waste heat goes into some other things like photons, directly gets emitted without any issue. We are not there yet. So as of now, the main issue is, we have to cool the cold end to lower than that. So somewhere around here, 300 or maybe even 200. So yeah, that's the issue. And that requires bonkersly large surface area. So either a huge radiator, or you can have one bypass option, that is multi-stage heat pump, like you do use that at basically ISS. Again, if ISS directly try to radiate human body heat to the outer space, yeah, it's not going to work. But they can have what we call ammonia refrigeration system that takes the heat, increases the heat in the condenser unit, and condenser unit dumps the heat into the vacuum of space. You can do that, but again, we are talking about a bonkers amount of heat, so you would need multi-stage one, so you can increase the temperature from here to here to here. And again, I don't think one system can just take heat from, let's say, 25 degrees Celsius and dump it to 125. I don't think we can get 100 degrees Celsius lift in even one. So you have to have multiple of them to give enough lift where the radiator side is small. But again, now you have the mass of the cooling system. So that is the primary hurdle, not anything else. Like everything else is sorted. Or again, you can design it like with thermally ablates, but it reduces lifespan, but which might be okay simply because you can travel to Mars in few months. 1 month, 2 months, 3 months is easy. So that's the design which NASA is actually currently working on. And Isaac, who was supposed to become the basically next director of NASA, he was also championing this. Was physically, this is the only option we have with the current technology, which again exceeds 900 and gets us into 2000, which again bare minimum. 2000 is bare minimum. As long as we can sort out the basically either multi-stage heat pump or super duper hyper lightweight radiators or hot electronics. So those are the ironical hurdle, like this curve is the hurdle that we are dealing with. Other than that, we are sorted. Like the size, the structure, the life support, and again, you do not need modular support. You do not need ginormous resources if you are only traveling for 3 months rather than 9 months or 5 months. So this is the future of humanities if we ever exceeds 2 light second. So there are some hurdles. So this was my presentation on basically nuclear electric propulsion. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free. And as always, thanks for watching.